Good afternoon and good evening. Thank you for attending this presentation. My name is Mingyu Yang, and I am from Yonsei University in South Korea. And today I will present our research on real-time urban microclimate simulations using multi-GPU computing. Before I start my presentation, I would like to briefly introduce my research topic. I am currently working in the multi-physics modeling and computational laboratory at Yonsei University under the advice of Professor Jung-il Choi. And I also participated in the NVIDIA A100 OpenACC GPU hackathon. My research focuses on CuFFT, especially urban microclimates, surrogate modeling, and high-performance computing through GPU parallelization. And I'm conducting research on CuFFT using a multi-GPU-based in-house code developed in the 2021 hackathon. Today, I'm going to introduce you to this code of which our group developed it. Our code is generating for solving urban microclimates such as wind velocity or temperature. Nowadays, urban is rapidly increasing with 68% of world population projected to live in urban areas by 2025. This requires rapid and high-resolution analysis of urban microclimate, possibly in real time in perspectives of smart city planning and urban air mobility. The CuFFT model is one of the good tools that provide high accuracy and captures the transient wind behavior, but it requires the management of a large number of grid points for accurate modeling of turbulence. As a result, many researchers are turning to HPC and highly parallel algorithms to address these challenges. But HPC has traditionally relied on a large number of CPU cores. So to overcome these CPU limitations, GPUs have gained attraction due to their superior computational speed. This results in faster feedback, enabling real-time simulations with meter-scale resolutions. As a result of this advancement, a growing number of urban studies are now utilizing GPUs. Building upon the foundational work on the facade from NCA and Concordia University CDFFT models, our research finds to navigate through the existing challenges, making advancement in computational efficiency and accuracy. In today's presentation, I will introduce the numerical method that constitutes our simulator and discuss its parallelization method using multi-GPUs. Then, I will demonstrate the conditions under which real-time urban microclimate simulation becomes feasible. Our study includes verification against a wind tunnel benchmark using an ideal state array domain and introduce a performance measurement method known as a real-time indicator. This indicator is evaluated under various conditions, including simulation area size, number of grid points, and GPU configurations. Finally, I will show results of realistic urban geometry in Seoul to validate its performance. First, I will show numerical method of our simulations. We use the conservation laws of mass, momentum, energy to represent the urban microclimate, which is called the incompressible continuity equation, the momentum equation, and the energy equation as shown here. In this point, how to find the velocity, temperature, and pressure solution of this Galvanic equation is very struggling point because it is very complicated partial differential equations. So to solve this, one of the major methods is called projection method developed by Chorin in 1967. In addition, our group developed the monolithic projection method with staggered time discretization called NPM-STD, extended version of Chorin's method to solve the Galvanic equations. The basic idea of this technique shifts the temperature field to the half-time step to decouple velocity and temperature. And the block LU decomposition is adapted to solve the Galvanic equations. So when it's done, this approach fully eliminates the need for iterative procedures in the overall algorithm. This means that this method allows fast computations while maintaining high stability. The only remaining and time-consuming hotspot area is three-diagonal matrix algorithm in equation 1 and 2, and the Poisson equation in equation 3. I will discuss it briefly at the section 3. And A key aspect of the urban microclimate simulator is how they incorporate buildings, which significantly influence wind patterns. Traditional approaches is often use body-fitted grid, as shown in the figure. However, this method requires a tedious task of manually generating meshes. To overcome these limitations, our study employs the immerse boundary method. This technique allows for straightforward implementation without the need to recreate meshes. Specifically, we adopted the Yang and Ballaras IBM model, which is known for its accuracy and ease of integration into large-scale simulator, such as supercomputer. Another issue is how to identify between building and wind areas using the raw data. For addressing this, we use GIS data from OpenStreetMap and the Korean National Geographic Information Institute. And we converted this data into a cell classification file using the sign distance function and approximate nearest neighbor algorithm, usually called ANN. The next session focuses on our multi-GPU implementation strategy. To adapt parallel computation in a multi-GPU environment, we employed CUDA Fortran and OpenACC with CUDA or where MPI and a GPU resident memory strategy. This approach allocates all memory directly to the GPU, thereby eliminating the need for CPU to GPU communication and enhancing computational efficiency. Also, we divided our physical domain for each GPU separately by domain decomposition method. This method divides equally so that it is guaranteed efficient calculation and prevent overload in each graphic card. One important thing is each GPU needed other GPU domains data for computation. So we opted for a select type one-dimensional decomposition, specifically chosen for its data communication efficiency in solving Poisson equations, a topic I will discuss on the later slide. Our computations were performed on the neural cluster located at the supercomputing center in Kisti in Korea, and each node of this cluster is equipped with 8 A100 NVIDIA GPUs. In our simulations, we incorporated 3 distinct approaches to leverage GPU computing capabilities. The first is the utilization of CUDA and OpenACC kernels employed for straightforward iterative procedures with each module. The second approach for solving equation 1 and 2 involves the Pascal TDMA algorithm, a highly scalable 3-diagonal matrix algorithm optimized for multi-GPU computing environment. Lastly, we employed the CuFFT library, specifically for discrete cosine transform-based Poisson servers for equation 3. Let's now focus on the first cornerstone of our implementation, the CUDA and OpenACC kernels. The OpenACC and CUDA kernels are responsible for executing most of the iterative instructions in our simulation. For simpler loop structures, the CuFFT kernel serves as an effective tool, but however, when dealing with more complex loop, optimization via tuning process becomes essential. A key element of our approach is the use of shared memory. As shown in the figure, the shared memory has superior bandwidth, but it is inherently volatile. So consequently, strategically moving data between global and shared memory at the start and end of the kernel significantly increase the overall efficiency of our model. The second implementation of our parallelization strategy is called Pascal TDMA. Traditional TDMA is essential for solving 3-diagonal matrices, but suffers from low scalability due to the need for inter-GPU communication or all-to-all communication. It's very computationally expensive. So to overcome this bottleneck, our group have developed a novel algorithm called Pascal TDMA. This algorithm decomposes a 3-diagonal matrix into modified submatrices and simplifies the 3-diagonal system to minimize data transfer between GPUs. Actually, this algorithm is already developed in CPU version, and it is already tested and validated in numerous CPU cores in Dr. Kim's research. And we have successfully developed a GPU accelerated version of Pascal TDMA while maintaining scalability, and it is projected to be 6.43 times faster and also 11.7 times more energy efficient than CPU socket when using NVIDIA GPUs. The third part of our multi-GPU implementation strategy focuses on the use of CuFFT, a DCT-based Poisson solver. Traditional method for solving the Poisson equation, such as conjugate gradient or Gauss-Seidel method, are iterative and therefore extremely time-consuming. Thus, the DCT-based Poisson solver proposed here does not use any iterations in solving equation 3, which allows for faster computation. Here, CuFFT was used to perform the DCT transform mentioned. CuFFT is a GPU-based FFT library provided by the NVIDIA HPC toolkit, and with some pre- and post-processing to the CuFFT method, DCT conversion can also be implemented. Our DCT-based solver addresses this inefficiency by using one-dimensional slab-type domain decomposition. This approach requires only two CuFFT computations, one in the X direction and one in the Y direction, along with the Pascal TDMA in the Z direction. This design eliminates the need for inter-GPU data communication in the FFT computations, so significantly improving the efficiency of our multi-GPU server. In the result section, we presented two distinct cases. Case A is an idealized domain for validation and testing, and case B is real urban geometry for implementation. Initially, we focused on case A, on idealized street array layout. The objective was to identify the minimum number of grid points required for both accurate simulations. So we tested 5 grid resolution configurations ranging from H/4 to 64, with the number of grid points maximum 1 billion. For validation, we examined the velocity profile midway between the 8th and 9th rows. The mean and RMS variations of streamwise velocity and temperature were compared to wind tunnel data, and all configurations, except those with haze greater than 4, demonstrated high accuracy. That means it is appropriate less than 5 meter resolution could guarantee physics of urban microclimates in most areas. Then, we aim to understand the interplay between grid configurations, simulation resolutions, and computational resources. To do this, we introduced a real-time indicator, R*, which serves as a measure of how the simulation's computational speed compares to real-world time. If R* is significantly greater than 1, then the computation is predictable and faster than real time. Our results obtained using different GPUs are plotted for specific grid configurations. And we found that using 8 A100 GPUs allowed real-time simulation with a spatial resolution of 1.25 meters over an area of 1.55 square kilometers. However, as the number of grid points increased, the performance was R* decreased significantly, indicating that advance in numerical method or hardware may be needed. Thus, the conclusion of case A is that a 5-meter scale is acceptable to represent urban geometry, and that a detailed relationship between grid point and simulation area and GPU number can be found. In our second case study, we selected a realistic urban area called the Yongsan district in Seoul, Korea. This area is very important in Korea because of its complex urban geometry, and it is a long-term planned route for urban air mobility. Including the buffer zone, the total simulation area is 10.49 square kilometers. To run our simulations on case B, we used 8 GPUs on a KIST neural server. And our real-time analysis showed that the simulation was achievable using a 4-meter grid resolution consisting of 42 million grid points. However, when the grid resolution becomes denser, it means that the grid point is proportionally increased due to the cost of dimension, so the computation speed becomes very low, like this. And when you look at the result, you can observe the phenomenon that occur in the urban microclimate, such as wind channeling effect, which the road between building makes a wind passage, and the sheltering effect, which large building block the wind, depending on the structure of the building. This simulation will allow users to make quick decisions in the future urban microclimate research because the calculation is very fast. So in addition, as better hardware becomes available in the future, users may want to consider whether the resolution should be closer or the simulation domain area larger. Based on the result of the case A, we have found that accuracy is already achieved when the grid is denser than about 5 meters. So in the future, in the case of simulating urban microclimate is in a street level, it will be better users may decide to increase the computational domain. Okay, this is the conclusion part. This study presents a multi-GPU based wind solver for urban microclimates. And through our validation using an idealized street array, we provide a quantitative analysis that makes the interplay between the simulation area, resolution, computational resources required for real-time simulation. We successfully performed 2.4 times faster than the real-time simulation of a 10 square kilometer area in Yongsan, Seoul, at a resolution of 4 meters using 8 NVIDIA A100 GPUs. Looking ahead, we see two main avenues for future research. First, the inclusion of additional practical modules in real-time analysis warrants consideration. And second, an additional tuning strategy for multi-GPU computing should be required. Our research has been just published in the Building and Environment Journal in September 23. So further details, you may refer to the published article for click the link or visit our laboratory website after the session is end. And I would like to extend special thanks to the NVIDIA KIST OpenACC hackathon staff and mentors and co-authors, Dr. Gunwoo, Tiantian Xu, Jungwoo Kim, and Dr. Ji-Hoon Kang in KIST, and co-developers, Professor Xiaomin Pan, Dr. Kia Kim, and hackathon team members, Sang-Yan Kim and Jiyoung Choi, and my academic advisor, Professor Jung Choi. And once again, I thank you for steps of OACS 23, our group's research. Thank you.